Hi everyone! This video looks at an example of calculating the metal ion concentration and the percent metal ion remaining in solution in an EDTA titration at the equivalence point. An EDTA titration is a complexometric titration where a metal ion is titrated with EDTA to form a complex. When EDTA reacts with the metal ion, this is called a formation reaction. The fractional amount of the EDTA species that primarily reacts with the metal depends on the pH. Therefore, the resulting metal ion concentration will be pH dependent. Our goal with an EDTA titration is typically to react more than 99.9% of the metal ion, which correlates to less than 0.1% remaining in solution. For the complexation reaction, we're showing a generic notation for the metal ion as M, having a charge of X+. It reacts primarily with the deprotonated form of EDTA known as Y4- to form a charged complex. For example, if the metal ion has a 2+ charge, then the charge of the complex will be 2 - 4, or -2. The species Y4- corresponds to the alpha fraction alpha 4, also noted elsewhere as alpha Y4-. If we know the pH of the reaction, we can use alpha and the analytical concentration of EDTA to obtain the molarity of Y4-. This makes it much easier to set up our calculations. In an EDTA titration, we have some volume of EDTA reacting with the metal ion, so we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and guides us as to how to calculate the concentration of the metal ion. In this generic millimole table, we're looking at the E row. Here we see that both the metal ion and EDTA go to 0, indicating that the reaction is stoichiometrically complete. When both the metal ion and the titrant go to 0, we are at the equivalence point. We essentially have a pure solution of the complex. Here, we have to consider the dissociation of the complex. How much metal ion will go back into solution as a result of that equilibrium? In order to calculate the metal ion in solution, we'll have to set up a mice table to evaluate the equilibrium of the complex. Our millimole table gives us the amount of complex, but this is in millimoles. We have to remember to calculate the molarity by taking the millimoles from the E row and dividing by the total volume. Then we can fill in the rest of the table. As a reminder, we will initially ignore the change in X, minus X, and apply our assumption that X is small compared to the molarity of the complex. After calculating X, we'll check this assumption. However, we cannot ignore a standalone X. So there are a few things we need to do to calculate X, which is the metal ion molarity we're looking for. We'll set up the mass action expression for K'd, the conditional dissociation constant, so we can fill in the values from the mice table. We also need to calculate the value of K'd. So first, we'll calculate K'F, the conditional formation constant, using alpha at the given pH and Kf for the metal ion. Then we can take the inverse of K'F to get the value of K'd. To determine if the reaction is complete, we calculate the percent of Mx+ remaining to see if it is less than 0.1%. Here we take the molarity of Mx+ remaining in solution and divide by the original molarity of the metal ion times 100. So let's take a look at our example. Our first step is to set up a millimole table, and the reaction at the top will be Mn2+ plus EDTA going to the complex, which will be Mn Y2-. The rows are I, C, E, initial, change, and end, and our units are millimoles. We'll calculate the millimoles to fill into the table. Starting with manganese, we have 10 milliliters of solution times the molarity of the manganese, which is 0.02310 moles of Mn2 plus, divided by liters of solution. The liters of solution will cancel, and we'll be left with milli and moles. We have 4 sig figs in our volume, 4 sig figs in our molarity, and our millimoles will be rounded to 4 sig figs. Doing the math, we have 10.00 times 0.02310 rounded to 4 sig figs gives us 0.2310 millimoles of Mn2 plus. Looking at EDTA, we have 16.50 milliliters of solution times its molarity, which is 0.01400 moles of EDTA per liter of solution. Liters will cancel, liters of solution, leaving us with milli and moles. We have 4 sig figs in our volume, 4 sig figs in the molarity, and this result will also be rounded to 4 sig figs. Doing the calculation, 16.50 times 0.01400 rounded to 4 sig figs gives us 0.2310 millimoles of EDTA. We can fill in our millimole table. We have 0.2310 for manganese, 0.2310 for EDTA, and 0 for the complex. We subtract 0.2310 from each reactant, and we add that amount plus 0.2310 to the complex. Manganese and EDTA both go to 0, and the complex goes to 0.2310. If we evaluate the E row, we see because both reactants go to 0, this tells us we're at the equivalence point. When we're at the equivalence point, we know we're going to have to set up a mice table, and when we use a mice table, we have to have molarity. So we'll calculate the molarity of our complex. We do that by taking the millimoles from the E row, 0.2310 millimoles of MnY2 minus, divided by the total volume, which is 10.00 plus 16.50 milliliters. The millis will cancel, leaving us with moles over liters, which is molarity. Looking at our sig figs, we have 4 sig figs in the numerator, 4 in the denominator, and our molarity will be rounded to 4 sig figs. Doing the math, 0.2310 divided by 26.50 rounded to 4 sig figs gives us 8.717 times 10 to the negative 3 molar MnY2 minus. We also have to calculate our conditional dissociation constant. We've got a couple steps involved. The first thing we have to do is calculate K'F, which is Kf 7.8 times 10 to the 13, positive 13, times the value of alpha at pH 10, which is 3.0 times 10 to the negative 1. Looking at our sig figs, we have 2 sig figs in Kf, 2 sig figs in alpha, and so our K'F will also be rounded to 2 sig figs. Doing the math, 7.8 times 10 to the positive 13 times 3.0 times 10 to the negative 1 out to 2 sig figs gives us 2.3 times 10 to the 13. K prime D, our conditional dissociation constant, is the inverse of that value. So 1 divided by 2.3 times 10 to the 13. The 1 is exact for sig figs. Our K prime F has 2 sig figs, so our K prime D will also have 2 sig figs. 1 divided by 2.3 times 10 to the 13 to 2 sig figs gives us 4.3 times 10 to the negative 14. Now we can set up our mice table so we can do the calculation. So the mice table is the dissociation reaction, Mn Y2 minus, dissociating to form Mn2 plus Y4 minus. This is a mice table, so the units are molarity. The rows are initial change and equilibrium. We already calculated our molarity, which was 8.717 times 10 to the negative 3. Our manganese and our Y4 minus are at 0. The change row is minus X for the complex and plus X for each product, which makes our E row 8.717 times 10 to the negative 3 minus X, and then X and X. So like we do for a lot of mice tables, we're going to ignore this change in X initially, and then we're going to go back and check. Let's write out our mass action expression for this dissociation. K prime D equals manganese, Mn2 plus, times Y4 minus, divided by the complex Mn Y2 minus. So we'll plug in our values. Our K prime D that we just calculated is 4.3 times 10 to the negative 14 equals X times X, or X squared, divided by 8.717 times 10 to the negative 3. We can cross multiply, and we get 4.3 times 10 to the negative 14 times 8.717 times 10 to the negative 3 equals X squared. And we'll take the square root of each side, and that will give us X. Looking at our sig figs, we have 2 sig figs for K prime D, 4 sig figs in the molarity. So when we calculate X, we'll round to 2 sig figs. So doing the math, 4.3 times 10 to the negative 14 times 8.717 times 10 to the negative 3, and taking the square root of that gives us 1.9 times 10 to the negative 8. If we take a look at our mice table, we notice that X has units of molarity, and it corresponds to our metal ion, manganese 2 plus. Now we do need to check the assumption just to make sure that it was a valid assumption. You can probably see just by glancing at it that the assumption is okay, but we still want to check. So we check the assumption by taking 1.9 times 10 to the negative 8 divided by the molarity in the ice table, 8.717 times 10 to the negative 3. The molarities will cancel. So doing the math, 1.9 times 10 to the negative 8 divided by 8.717 times 10 to the negative 3 times 100, we need to round to 2 sig figs, and we get 2.2 times 10 to the negative 4%. So that tells us that our assumption is okay because it's less than 5%. So the molarity of the metal ion left in solution is 1.9 times 10 to the negative 8. We have one more step, and that is to determine if the reaction is complete. So we want to calculate the percent left in solution. Be careful here because this goes back to the original molarity. So we take the molarity that is left in solution, that's 1.9 times 10 to the negative 8, divided by the original molarity, which was 0.02310 times 100. This is not the same thing as checking the assumption. We have 2 sig figs in our numerator, 4 in the denominator, 100 is exact, so the percent remaining in solution will be rounded to 2 sig figs. Doing the math, 1.9 times 10 to the negative 8 divided by 0.02310 times 100 gives us 8.2 times 10 to the negative 5%. Our threshold for reaction completion is 0.1%. So because this value is less than that, the reaction is complete.